Hey, it's Dr. J. Today we're going to do 3.7, the inverse functions, part 1. So before I do any actual problems, let me just talk a little bit about the abstract. This is what's called a map. So a function takes an x value from the domain and sends it over to a y value in the range. Yeah, that's the idea of a function. Okay. Now, keep in mind that you can't have something like this. You can't have one x getting sent to two different y's. If these y's are different, y1 and y2 are different, you can't have the same x. This would not be a function. Right? If this happens. So if one input corresponds to two outputs or more, anything more than one, so 2, 3, 4, I use 2 as a simple example, then this would not be a function. Okay. However, it is okay to have two different x's get sent to the same y value. That's okay. This is a function. That would be okay. That would just mean that f of x1 is equal to y and f of x2 is equal to y. This means that you have two different outputs. Sorry, I meant two different inputs with the same output is okay. That's okay. All right. We would still say that this is a function. All right. So the rule doesn't seem equitable, on the x's and the y sides. If I were to take this graph and turn it around, where you have one input and two different outputs, that would not be a function. We've gone over this going all the way back to the original section 3.1, back before the pandemic sent us all home. So today what we're going to do is we're going to talk about inverse functions. An inverse function essentially reverses the order and takes the y values and sends them back from whence they came. So this is what we call the inverse. The y value is being sent back to the original x value that it came from. The inverse must also be a function. And so what does that mean? That means that this can't happen. So you can't have two different x's with the same y. For the same reason that you can't have two y's with the same x. And so what we're going to do is we are now going to further restrict our idea, we have relations. We have a subset of the relations called the functions. And then we have an even smaller subset called the one-to-one functions. And this is what we're going to talk about today, one-to-one functions. So the definition. You first have to be a function. A function f is called one-to-one, sometimes abbreviated 1-1 or 1:1. These are some abbreviations for one-to-one that I might use today. If each input corresponds to exactly one output, and each output corresponds to exactly one input. In other words, going back to my abstract map, 1x, 1y, 1y, 1x, nobody can have two values associated to one value. So this is a much more equitable way of thinking about what it means to be a function. Every x corresponds to exactly one y, and every y corresponds to one x. Via f, the f is the one-to-one function. Okay. Let's see some examples of a one-to-one function. This is just an abstract way of thinking about it. We're not actually going to draw our graphs like this. We're going to draw our graphs like this. X and y in the typical way that we draw a function. Example 1. Which of the following graphs are one-to-one functions? I'm getting my graph planes ready. And let's do several different versions of this example. Don't really worry about how I got these graphs. I got all of these graphs by doing the techniques from 3.5 and 3.6. So these are all functions that you might have seen in a previous lecture. Okay. So remember, each x should correspond to exactly one y, and each y should correspond to exactly one x. So if you can find an x that has the same y value for two different x values, This is what we call the horizontal line test. If a horizontal line touches the graph more than once, it's not one-to-one. So this function is no. It is not one-to-one. Because I have two different x values corresponding to the same y value, whatever this y value happens to be. I have two different x values corresponding to the same y value. Okay. So let's try it here. We have an x value. You have a y value. You have a horizontal line. It only touches it one time. Yeah. If you take a different x value, you take a different horizontal line, it's again only going to touch it one time. So this is, yes, this is a one-to-one function. This is a one-to-one function. You could easily just go across the graph and draw horizontal lines like this. Yeah. So each horizontal line touches the graph only once. So this is a one-to-one function. Yes, one-to-one. All right. This is not even a function. It's a circle, or it's actually an ellipse. It's a sort of stretched out circle. I'd be honest with you, I was actually trying to draw a circle, but I just drew it badly. If it's not a function, then it's immediately not one-to-one. Right. You must first be a function before you can be a one-to-one function. So if something's not a function, it's definitely not one-to-one. Okay, this one, draw a horizontal line through it. If it touches the graph more than once, that's no, it's not one-to-one. Yeah, two different x's. Doesn't matter what I call them. I could call them x2 and x1. You could call them A and B. It really doesn't matter. If you have two different inputs and they produce the same y value, then that's not one-to-one. Now this one is real close. It's about to turn around and go the other direction, but we've removed the bottom half of this. Remember, this used to be a sideways parabola back in the section that we did on conic sections, but we have truncated it, or we've trimmed it so that it's one-to-one, so that when you do the horizontal line test, this is yes, this is a one-to-one function. Okay. So the horizontal line test is much like the vertical line test. The vertical line test, VLT, was done back in section 3.1 review. Vertical line test will tell you whether it's a function or not. And if it fails the function test, if it fails the vertical line test, I don't even bother giving it the horizontal line test. Okay. So we have what we often call the rule of three, which really means that there are three ways to view a function. The first way we just saw, graphing. The second way is by a table of values. And the third way is by a formula. So graphing, use the horizontal line test. Check. We've already done that. Next, we're going to look at what does a function look like if we look at it as a table of values. Trying to get the screen to focus. Come on, focus. Not good enough. You guys see that? All right. So next we're going to talk about table of values, and then we'll do the formulas in a minute. A table is just a numeric representation of a function. Instead of drawing the points, I'm just illustrating them in a table. I'll fill out the table in a second. So we've got our table of values. It's really blurry. Let's see if I can get the blur to go away. Sometimes this helps. There we go. Okay, so which tables represent one-to-one functions? Well, we're essentially going to do the horizontal line test without actually drawing a horizontal line. In fact, you never actually have to draw the line. You can just think about what a horizontal line means. A horizontal line means that you have the same y with two different x's. That's what a horizontal line is, right? Think about a horizontal line. You have a horizontal line. The y value is fixed. It's whatever that horizontal value is. And then you have two different x values corresponding to the same y value. All right? Picture of that would look like this. You have x2, comma, y. And then you have x1, comma, y. You have two different x's, but they both touch the same exact y value. So just look at these. If you see the same y value with two different x's, this is not one-to-one because it has the same y value with two different x values. So we can just go through and by inspection, look and see there is no repetition. You never have the same y value. So this is one-to-one. As long as you never see the same y value repeating, then it is 1-to-1. All right? Y values do not repeat. You want an easy way to inspect your tables. So we have a yes, we have a yes, and we have a no. This is not 1-to-1. So I guess it says which tables are 1-to-1. So I would say B is 1-to-1 and A is 1-to-1. There can be more than one answer. Okay. Finally, our third way is if there's a formula. In other words, an equation. An equation is a formula for a function. Means the same thing. Now this is a little trickier. Okay. So I'll do a few different examples. Okay. Maybe I'll call this one G. I want them all to be slightly different names. So this one's called F. This one doesn't have a specific name. It's just called Y. All of these are Y equals if you want to rewrite them. And this one's called G. So when you have an equation, it's your choice. One, you could draw a graph and use the horizontal line test, HLT. Or two, you could try to find a repeated y value for two different x values. Now, sometimes the first method is the easiest method if you already know how to draw the graph. All right. If you don't, or if you just don't want to spend the time drawing the graph, in the last couple sections, I spent a lot of time showing you different techniques for drawing graphs, so you can use those. But you might not want to. You might say, well, I don't want to draw a graph. I want to find another way. Well, you can do that. Your option is to try to find a repeated y value. All right. And you might not find it. If you can't, if you do lots of different examples and you can't find it, you could assume, or you could, bet, I guess, you'd be sort of gambling that it's probably a one-to-one function. So method number two is a little risky. All right. Method number one is more of a less risky. Yeah. I mean, everything is risky. You're always going to have something can go on. So how about this one? X squared plus 3. All right. I know my mother function is x squared, and it's been shifted up 3 units. So I'm going to draw a graph. It doesn't have to be a very good graph. It's a parabola shifted up 3 units. Definitely not one-to-one. See? Horizontal line, 2 different x's give you the same y value. So no. Okay. All right, how about this one? Y equals x cubed minus x. Not so easy. This graph's a little bit more complicated to graph. All right, if it was x cubed minus 5 or x cubed plus 10 or something like that, it would just be a vertical shift and it might be a little easier. All right, this is not a simple transformation. Yeah, so it's not going to be a 1-2 graph like I was able to do here. So for this particular example, I'm going to try to find two different x's that give me the same y. All right. If I can't, I'll try several attempts, and if I can't find it, well, then I'm going to say, oh, you must be 1-to-1, right? Because I can't seem to find you violating the principle of the definition of 1-to-1. All right. So the graph is not easy. I mean, it's not impossible, but it's not easy. So I'm going to try to find two x's that give the same y. And when I give you these problems in this section, it should be relatively simple to find two different x's. Let's try 1 and -1, or 1 and 0, or something like that. Something relatively simple. So let's try 1. We got 1 cubed minus 1. That gives us 0. Yeah. So on our table, I'm blocking my table. On my table of values, I've got x is 1 and y is 0. All right. Now look carefully at this. Can you find another x that also gives you 0? That's all you have to do. If you can find another x that gives you 0, then this function is also not 1-to-1. I think I can hear you through the internet. Everybody's saying 0, 0. Yeah, look, 0. 0 squared minus 0. Well, that's equal to 0. So I just got it. I've got two different x's that are giving me the same y value. And so this is also not 1-to-1. Okay. Now that we've done this, you can actually kind of see what the graph looks like. It kind of looks like, actually, I think there's a third x that does it. Turns out that -1 also gives you 0. I know I've already determined that it's no, but I want you to know that you could have chosen some other numbers. So suppose I chose -1. This is a good idea to try 1 and -1. That's what would have done it over here. See, over here, 1, -1, those two x's. So if you're looking for a no, that's a good place to look. All right. So you get -1 plus 1, which is equal to 0. So it turns out that this function violates it 3 ways. It gives us a pretty good idea of what the graph looks like. The graph crosses the x-axis 3 times. There are 3 different x's that all give you the same y value of 0. So sometimes trying one method kind of leads you into the other method anyway, even if you're trying to avoid that method. All right, moving on to the next one, square root function, x plus 4. Just a quick review of the last couple sections. This would be a shifting left 4 units. So what would the graph look like for this? 1, 2, 3, 4. Now in this section, at least at the beginning of this section, we're only on example 3. I'm drawing the graphs very quickly. You'll have to refer back to section 3.5 and 3.6 to see all the details of this. All right, I guess there would be a second point here. That would be 0, 2. That would be the y-intercept, and then the x-intercept would be -4. So if you already know how to do the graph, you can just do the horizontal line test. Yeah, and so yes, this is a one-to-one function. Okay. So this one's yes. These are both no's. Going back to the mother functions, identity is one-to-one almost always. There's only one exception. The identity is not one-to-one. The exception would be a horizontal line is not one-to-one. So if you take the identity function and you multiply it by 0, you give it a 0 slope, you end up with a horizontal line. That's the only linear function. Another name for the identity is the linear function. It's the only example of a linear function that is not one-to-one. So almost always the linear functions are one-to-one. Lines. Okay. Number 2, absolute value. The absolute value is never one-to-one. Yeah. The shape always looks like a V. It is never going to be one-to-one. The quadratic. The quadratic is never one-to-one. Yeah, it looks like a U shape. It's never one-to-one. The square root. Always one-to-one. Square root function's always one-to-one. Never have to worry about that. The cubic. Sometimes one-to-one. Sometimes not. Yeah. So you should graph to be sure. Sometimes it's not. So the cubic looks like this. That would be the one-to-one version, but sometimes it's not. Sometimes it looks like this. And if, like in the example we just did, if the cubic does a double turn like that, it's not going to be one-to-one. All right, that would be the violation. Number 6, the cube root. That's going to always be one-to-one. Yeah. What the cubic does, this little curve here, the cube root will never do that, because if you had a cube root that looked like an S, it would not be a function. This is not a function. I should have drawn those vertically, huh? Yeah. So this is not a function. This will never happen. So the cube root will always look like this, and it's always going to be one-to-one. All right, so this never happens. if this did happen, we would have kicked it out of chapter 3 way back at the beginning of chapter 3. 7, the reciprocal. That's always going to be 1 to 1. Remember what the graph of the reciprocal looks like. And then the reciprocal squared, its cousin. That's never 1 to 1. So the reciprocal squared is never 1 to 1. All right, so some people like to just look at their handout of the 8 mother functions and go through and identify which ones are potentially 1 to 1 or could possibly be 1 to 1. Personally, I just memorized the nevers and the alwayses. Always and never. The sometimes is not worth memorizing because it's a sometimes. You can't memorize something that's sometimes true. So you just have to handle those on a case-by-case basis. Let's try another one. Now that we got the idea. Example 4. Determine which equations represent 1-to-1 functions. So y equals negative 6x plus 5. F of x equals 9 over x. F of x equals the cube root of 4x minus 2. Or let me call that g of x. I'll use different names. G of x. Y equals 8. H of x equals the absolute value of x minus 4. And y equals x cubed plus 7. So we can do this just by looking at the equation and remembering or comparing it to the different types of functions that we have. So this is a line. It's not horizontal. You can tell because it has a slope of negative 6. Yeah. So I kind of know that what the line's going to look like in my head. It looks like a line going down like this. The slope is negative 6. I'm not spending a lot of time on the details. The 5 is the y-intercept. The slope is negative 6. So I know this is a line. I know that it's not horizontal. And so I know it's 1-to-1. So yes, this one is 1-to-1. I'm just going to mark yes and no next to each one, whether it's 1-to-1. In your homework, only pick the yeses, okay? Just ignore the no's. Okay, this is a reciprocal function. Reciprocal are always 1-to-1. So yes. This is always 1-to-1. I don't even have to draw the graph. I know that it's always 1-to-1. This is a cube root. Okay, memorize which ones are always. It's like getting a free answer on the next test. So that's always 1 to 1. Cube roots are always 1 to 1. So this one's also yes. This is a 1 to 1 function. Here. This is the same as 0x plus 8. Yeah, if you don't see an x, it means the slope is 0. So that is a horizontal line. A horizontal line is not 1 to 1. So this one is a no. If you drew the graph of this function, it would pass through 8, and it would just be a horizontal line passing through y equals 8. I don't know if you can see that. That's supposed to be 8. Graph. All right. This is an absolute value. Absolute value is never 1 to 1. So that's a no, automatic no. Absolute value is never, ever going to be 1 to 1 because it always looks like the letter V. I don't even have to spend any time graphing it. I know that this will look like the letter V. Those are supposed to be absolute value bars. I feel like I'm making them worse every time. There we go. That looks pretty good. All right. The hardest one is the last one. Cubic is sometimes 1 to 1. Okay. So this is a cubic with a vertical shift. So draw the graph. It doesn't have to be very good. It just has to be a rough sketch of what the graph would look like. It would look like the mother function with a vertical shift up 7 units. So this would be a 1 to 1 function. This would be a yes. Yeah, see? Yeah. If you draw a horizontal line, it will never touch this graph more than once. If you want, there's sort of a clue as to whether a cubic ends up being not 1 to 1. That would be if the 7 had an x on it. Yeah. If this was x cubed plus 7x, what would happen is the cubic would turn back around and it would have 2 intercepts, and that would cause it to not be 1 to 1. Okay. Or you could just play around with it. I actually want you to suffer a little bit. I want you to do all the graphing from the previous section, and then you get used to the idea. The more you experiment and the more you get familiar with the different functions, the easier these problems are going to be. Okay, so the first 4 examples are all about what does it mean to be 1 to 1. And now we can start talking about inverse functions. An inverse function. I've kind of abstractly described what the inverse is. It's sort of a map that goes back to where you came. You can think of it as a list of directions that tell you how to get back home, right? But I'm going to give you a more precise definition. If f is a 1 to 1 function, so you first have to start with a 1 to 1 function. Then f negative 1 is called the inverse function, given by f of a is equal to b if and only if f inverse of b is equal to a. In other words, if the function sends a to b, I'm using a and b intentionally instead of x and y. A is a specific x value, and b is a specific y value. All right, so a is over here in the domain, and b is over here in the range, the y's. So if f sends a to b, then f inverse sends b back to a. This is the symbol for inverse. It is not an exponent. That's very important that you don't accidentally think this means f to the -1 power. Unfortunately, it looks like an exponent simply because we don't have anywhere else to put it. So we put it there for lack of a better place to put it. So there it is. There's your inverse function. Let's do a problem involving a inverse function. Suppose f is 1 to 1, and f of -5 is equal to 6. Find the value of f inverse of 6. All right, well, -5 is our A, 6 is our B. So using the definition, if the function sends -5 to the value 6, then the inverse function sends 6 back to -5. And you're looking at me like, is it really that simple? And I'm saying, yes, it really is that simple. For now. Why don't I squeeze one more on here? If f inverse of 9 is equal to 7, what is f of 7? Well, it's 9. Again, moving forward, we're always going to assume from now on that if I give you a problem of this variety, that I'm assuming that it's a one-to-one function. Otherwise, I wouldn't be able to say this so clearly. Okay. The light is getting strange in here. Hi, I'm back. This is what we refer to as a pointwise function. It's only giving us one particular point on the graph. We could do some examples using a table. So suppose I give you a function, and it should be a one-to-one function in terms of a table. So let's find the following values. Let's find f of 2, f of 2, f of 2 is 1. So what would f inverse of 1 be? That would be 2. What is f of 4? F of 4 is 3. So what is f inverse of 3? F inverse of 3 goes back to being 4. So these are called evaluations. All right. We could also find some solutions. Suppose f of x is equal to 7. Using the table, I could solve for x. So if f of x is equal to 7, I'm finding the row in which y is equal to 7. That's really what this means. Find x if y is 7, and you can clearly see that x is 3. Now, the main difference between an evaluation and a solution is a solution must have the variable that is given in the problem. So the problem is giving us the variable x, so we must answer x equals 3. And in my last example, I'm going to do the same thing using the inverse function. So f inverse of x is equal to 5. Now this is weird because I'm going to answer it using the letter x. But over here, it's actually going to be y. So let me teach you a trick. Whenever I give you a function table, at the very bottom of your table, here's a trick for the variables. Put x in the y column and put f inverse in the x column. This will help you to read your equation in the right order. So this says f inverse is equal to 5. So I want to know when is my f inverse equal to 5. And then I'm solving for x. So x is going to be 0. Even though this is in what we used to call the y column, you got to kind of get that out of your mind. We are not fixed. The variable is not necessarily y. This is what we used to call y. It is now x with respect to the inverse function. And I know when the first time I heard that, I was like, what? What used to be y? You're now calling x? Well, you're driving me nuts, Dr. Jordan. But it's just the way it is. You know, you just have to deal with the complexity of it. Okay? It will become clearer over time. So not all things are clear the first time you see them. So this x value is 0 in the what used to be called the y column of our table. Just deal with that. We only have time for one more for this section, and I'll get it up there on YouTube as soon as I can. So example 8.